high in the mountains of Jammu and Kashmir, India built a railway bridge where even reaching the construction site was a challenge. The Chenab River cuts through this valley hundreds of meters below, and across that open gap, engineers had to place one of the most difficult railway structures ever built. This is the Chenab Rail Bridge, the world's highest railway bridge, standing 359 meters above the river. But the real story is not the height alone. It is the question behind it. How do you build a railway line across the Himalayas when the ground is unstable, the winds are violent, and there is no easy way to bring heavy steel into the valley? In this video, we'll break down how India turned a dangerous Himalayan gorge into a working railway route. For decades, the railway line to Kashmir was one of India's most difficult infrastructure dreams. The plan was to connect the Kashmir Valley to the rest of the Indian railway network. But on the ground, the route had to pass through mountains, tunnels, unstable slopes, deep river valley and sections. The larger project became known as the Udhampur-Srinagar-Baramulla Rail Link, or USPRL. It runs for 272 kilometers through Jammu and Kashmir and includes 36 tunnels stretching for 119 kilometers, along with 943 bridges. It was built to create all-weather rail connectivity between the Kashmir Valley and the rest of India. But one part of the route stood out from everything else: the Chenab River Gorge. Here, the river cuts through the mountains between Bakal and Kauri. The valley is wide and difficult to access. Building a normal railway bridge here was out of the question. There was no simple place to put support columns in the riverbed. The bridge had to cross the valley in one huge movement of steel, while standing hundreds of meters above the water. That is how the Chenab Rail Bridge became the defining challenge of the entire route. The bridge is 1,315 meters long, with a main arch span of 467 meters, and it stands 359 meters above the riverbed. That makes it the world's highest railway arch bridge. It is also about 35 meters higher than the Eiffel Tower. But height was only the visible part of the problem. The real difficulty was what came before the bridge could even rise. Engineers had to bring thousands of tons of steel into a remote mountain gorge. They had to build on fractured Himalayan rock. They had to design for strong winds, seismic forces, difficult temperatures, and the movement of trains. And they had to do all of this in a place where one mistake could delay the project for months. First, they had to reach the site. Before the first major steel section could be lifted, engineers had to solve how they would build a mega bridge in a place where heavy machines cannot easily reach. The Chenab Bridge sits in terrain where access itself became a construction project. The official figures show the scale of that early work. The bridge construction involved 10 lakh cubic meters of earthwork, 66,000 cubic meters of concrete, and 26 kilometers of motorable roads. It also required the fabrication of around 28,660 metric tons of steel. Those 26 kilometers of roads were the routes that allowed cranes, drilling equipment, workers, concrete, steel plates, bolts, and temporary structures to reach the gorge. This was because the full bridge sections could not simply be driven through the mountains in their final form. The curves, slopes, and access limits meant much of the work had to be broken down into manageable parts. The executing agency was Konkan Railway Corporation, working for Northern Railway. The contractor was the Chenab Bridge Project Undertaking, a joint venture involving Ultra, Afcons, and Versal. The viaduct and foundation design involved WUSP Finland, while the arch design involved Leonhardt, Anderun partner from Germany. Other expert groups worked on slope stability, seismic analysis, foundation protection, and proof checking. And under all of it was the Himalayan rock. The Himalayas are young mountains in geological terms. They are active, folded, fractured, and exposed to landslides in many areas. At Chenab, engineers were anchoring it into steep slopes, where the structure had to push massive forces into the sides of the gorge. The bridge was designed for earthquake forces in India's highest seismic zone, Zone V. It was also designed for high wind speeds, up to 266 kilometers per hour, and for a 120-year design life. That meant the foundations had to become part of the mountain system. Once the site and foundation problems became clearer, engineers still had to choose the right bridge form. A railway bridge cannot move like a light pedestrian bridge. Trains need stability. The track must stay aligned. The deck must handle heavy loads and vibration. At Chenab, the bridge also had to cross a deep valley without support from below. That is why the final structure became a steel arch bridge. An arch works by pushing forces outward into its supports. Instead of relying on tall piers from the riverbed, the arch carries the loads through its curved form and transfers them into the two sides of the gorge. For Chenab, this was the logical answer. The valley was too deep for normal support from below, but the mountainsides could be used as the main anchoring points if they were properly stabilized. The arch itself became one of the most important parts of the project. It weighs 10,619 metric tons, and it is made from steel boxes that were designed to be filled with concrete to improve stability. The bridge also had to face wind in a very specific way. At that height, above a deep mountain gorge, wind does not behave like wind over flat land. Special wind tunnel testing was carried out, including topography testing and aeroelastic model tests, to understand how wind would affect the bridge. The tests showed unusual wind behavior, including vertical inclination in the mean wind velocity and turbulence intensity that changed widely depending on wind direction. So the bridge had to be strong, but also predictable. It had to resist wind and seismic forces. It had to carry trains at a design speed of 100 kilometers per hour. It had to remain safe for decades in a harsh location. But designing the arch was one thing. Building it across open space was the harder part. The Chenab Gorge left engineers with a direct problem. The arch had to be assembled above the valley, but no crane sitting on the ground could simply reach across the gap. Scaffolding from the riverbed was not a practical solution at that height. The steel had to be carried through the air. So engineers used a cable crane system. Konkan Railway says a cable car system was designed and commissioned for construction of the arch portion. It used 54mm cables laid across the river valley and connected through pylons on either side. The pylon height reached 127 meters. The main cables had a span of 915 meters, with pylons at the ends. The cable crane traveled back and forth using suspension and traveling cables, and each traverse had a load-bearing capacity of 20 tons per hook. Two such systems were installed side by side and could work together in tandem. This was how the bridge began to grow across the gorge. Steel blocks were lifted from the work areas and moved into position over the valley. The arch was erected by the cantilever method, with the two halves advancing from opposite sides. Reports say the suspension cable crane could lift one 35-ton steel block at a time, and the arch halves were held with steel cables attached to the bridge foundations. Then came the closure. On April 5, 2021, Indian Railways announced that the arch closure of the Chenab Bridge had been completed. A final 5.6-meter steel piece was fitted at the highest point, joining the two arms of the arch that had been extending toward each other from both banks of the river. Until the two sides met, the structure was still in a temporary construction state. Once the arch closed, the bridge could begin moving toward its final form. But closing the arch did not mean the railway was ready. After the arch closure, there was still more work. The bridge still had to become a railway. By 2025, the bridge had become part of a completed rail connection. On June 6, 2025, Prime Minister Narendra Modi inaugurated the Chenab Bridge, along with the Anji Bridge, and dedicated the Uspral project to the nation. The same official release described the Chenab Bridge as the world's highest railway arch bridge and said it would help improve connectivity between Jammu and Srinagar.